Hello, my name is Aaron Alvarez, and in this presentation, I'm going to speak about an exciting paper published by the journal ACM Transactions on the Internet of Things named MakeSense, an IoT testbed for social research of indoor activities. First, let's provide a brief overview of the paper. As we know, there has been increased interest in deploying Internet of Things devices to study human behavior in places like homes and offices. These devices can be deployed in a laboratory or in the wild in natural environments. The latter allows behavioral data to be collected that is not contaminated by the artificiality of a laboratory experiment. Additionally, using IoT devices in ordinary settings brings the benefits of reduced cost compared to laboratory experiments, and less disruption to participants' daily routines, which in turn helps recruit them for research. However, in this case, it is essential to have an IoT infrastructure that can be easily and quickly installed and from which real-time data can be collected safely and easily. In this sense, the paper I will discuss today presents MakeSense, an IoT testbed that enables real-world experimentation for large-scale social research on indoor activities through real-time monitoring and situational awareness applications. Now, let's discuss in more detail what is MakeSense. MakeSense has been designed to provide an infrastructure that enables real-world experimentation for large-scale social research of indoor activities through real-time monitoring and situation-aware applications. The use of cloud infrastructure for data monitoring and storage, as well as for data analysis and data visualization, introduces benefits for scalability, ease of extension, reliability, and manageability. The design of the self-manufactured IoT device developed for MakeSense leverages commodity ambient sensors and moves away from intrusive IoT devices such as cameras. Furthermore, due to its multi-radio setup via Bluetooth, low energy, and Wi-Fi, MakeSense allows ad hoc self-manufactured or commercial sensors to be added and interface with the IoTX acting as relays. MakeSense adopts a client-server-like paradigm. As can be seen in this image, all of the sensing devices deployed in indoor environments such as homes or offices serve as clients that collect physical environment data that are sent directly to the server backends via LWM2M through broadband internet. The server backends can be hosted on a private cloud or an on-premise dedicated server with enough capacity. Besides receiving data from sensors and storing them on persistent storage, the server backends also provide support for administration and visualization through web applications. MakeSense features both commercial, off-the-shelf, and self-manufactured IoT devices. These IoT devices can be directly connected to Wi-Fi access points or benefit from the capability of the IoTX Wi-Fi modules to operate in both station and access point modes, as well as from their onboard BLE module. Both static and mobile COTS and self-manufactured BLE and Wi-Fi based sensors can thus be utilized by the IoTX, augmenting their onboard default set of sensors and enabling opportunistic sensing interactions. Data captured by the IoT devices are collected from houses or buildings relying on readily available Wi-Fi networks and Internet access, thus benefiting from higher reliability, lower interference, and higher throughput as compared with other radio technologies that would need to be deployed. MakeSense supports data transmission and device management over LWM2M, which is used together with the Constraint Application Protocol, an application layer protocol designed for resource-constrained IoT devices. By using Wi-Fi and Constraint Application Protocol via a UDP protocol, high temporal resolution measurements can be collected, limited only by the sample requirements of the physical sensors. Furthermore, MakeSense implements security at the communication level with datagram transport layer security and pre-shared key authentication, and all of the data are encrypted with advanced encryption standard 128-bit before transmission. The server side is deployed on a private cloud that supports persistent storage of sensor-generated data via databases deployed on virtual machines. The infrastructure is based on OpenStack, with storage distributed identically between these volume-based and document-based object storage services. Moreover, front-end interfaces for monitoring, administration, and visualization are deployed inside VMs that can be easily accessed anywhere through the Internet via web browsers. MakeSense introduces a reliable storage solution by providing data backup and replication. On the remote cloud infrastructure, data storage serves two purposes: data post-processing and real-time data visualization analysis. For data post-processing, the open-source databases such as PostgreSQL and MongoDB are used. In the latter case, the open-source search engine Elasticsearch is used together with its dedicated visualization platform, Kibana. The following picture shows the software architecture of MakeSense. Since LW end-to-end adopts a client-server architecture, an LW end-to-end client was developed running on the IoT Act, interfacing with embedded sensors and actuators, and communicating via COAP with an LW end-to-end server. By leveraging LW end-to-end and IPSO smart objects, end-to-end applications are deployed on the cloud and operated using standard APIs. LW end-to-end clients maintain their registration and thus their current availability, as well as the list of their objects and resources, via an LW end-to-end server registry, accessible via HTTP request. As shown in the picture, two end-to-end applications were designed, interfacing with the LW end-to-end server via HTTP, one for building images and downloading firmware over the air to the IoTX and the other for handling data collection from the IoTX. The LW end-to-end server publishes via Advanced Message Queuing Protocol to a RabbitMQ message queue broker. It publishes both control messages on one queue exchange and live sensor measurements on another queue exchange. MakeSense supports a range of connectivity options enabling virtually any sensor capable of interfacing with BLE and Wi-Fi to be used in combination with the IoT acting as a gateway. Given both the non-intrusive design of the IoT and the secure communication and storage, the security and privacy of the participants of the study is preserved. In the market, there are many electronic modules that can be used to build sensor suites for different measurements. One example of such development is the IoT Egg designed and developed at the 5G Innovation Center at the University of Surrey. The IoT Egg is encapsulated in a box as can be seen in the picture. It has a temperature and humidity sensor board that is managed via an I2C interface and sampled periodically by the client application deployed on the ARM core. It also has a light sensor managed via an I2C interface. This sensor is used to sample ambient light. Finally, a microphone breakout board is used to sample noise levels in the environment on another ADC channel, and the values are converted to sound pressure level decibels. The IoT Egg has been equipped with a BLE module that allows additional COTS or self-manufactured sensor suites to be added and connected to the IoT Egg to enable further data collection. Furthermore, the Wi-Fi module allows both operations, either as a Wi-Fi access point and as a Wi-Fi station, or both together at the same time, thus enabling additional Wi-Fi based sensors to be connected to the IoT for relying data. There is also a wide selection of commercial products, ranging from elementary ones like temperature and humidity or accelerometer sensor suites to more sophisticated ones like energy monitors, pet tags, smart locks, and wearable trackers. In the case of MakeSense, the BLE module built in both the wristband and the IoT Egg were used to capture the received signal strength indication distribution over time to have a rough localization method. This allows to estimate how close the wristband is to the IoTX placed in different building locations based on the received signal strength distribution measured by each IoTX. The Mi-band and the current cost energy monitor presented in this image are only two examples of integrating commercial sensors with MakeSense. MakeSense aims to facilitate data collection through easy to set up, fast, and reliable Wi-Fi networks. Furthermore, the ease of adding other types of Bluetooth or Wi-Fi enabled sensors and actuators is supported by the IoT, which can be used to relay measurements or control messages back and forth from the cloud infrastructure. For MakeSense to provide most of the desired features of an IoT testbed, such as remote management, pre-programming, customizable data collection, live query for location and connectivity, security, etc., the LWM2N over COAP is used along with encryption with TTLS and pre-shared keys authentication. A full-fledged LWM2N client has been developed, featuring the following LWM2N objects: LWM2N security, LWM2N server, access control, device, connectivity, monitoring, firmware, location, and connectivity statistics. This allows for configuring the device remotely and providing features such as setting secure mode, default device lifetime notification period, static GPS coordinates, time synchronization, factory reset, and remote reboot. Furthermore, network and connectivity parameters and statistics can be inquired from remote, such as Wi-Fi RSSI, IP addresses, and configuration. As can be seen in this image, on the server side, the LWM2N server is able to access not only the standard LWM2N objects, but also the additional IPSO smart objects. All of the cloud data management is handled via a RabbitMQ message queue broker deployed on a VM and secured with access control and authentication mechanisms. The broker has three main subscribers listening for data: the data collector service, the data visualization service, and the historical data store service. The data published by the brokers comes from two main sources: the control messages and the live data streamed from the sensors. The data collector end-to-end application running on a VM as a reliable and always-on Linux service has been developed in Python. This application listens for the LWM2M client registrations to the LWM2M server via RabbitMQ, where the server publishes registration messages. The application is thus aware of when devices come online and when data collection from the IPSO smart objects can be started by sending requests to the LWM2M server via the HTTP interface. MakeSense relies on the open-source search engine Elasticsearch and its dedicated analytics and visualization platform Kibana for data visualization and analysis. Elasticsearch supports scalable and real-time search with an HTTP web interface and schema-free JSON documents. Kibana provides visualization capabilities on top of the large volumes of data indexed by an Elasticsearch cluster. As can be seen in this image, users can create different kinds of visualizations such as line, bar, and scatter plots, pie charts, and maps with the indexed data. Furthermore, users can combine different visualizations to create customized dashboards, which can be shared via the web or integrated as HTML frames into existing web applications. In this presentation, I discuss a paper that presents MakeSense, an IoT testbed that facilitates social studies of indoor activities. As we could see, MakeSense is a testbed that is non-intrusive, cost-efficient, and easy to deploy, safekeeping the security and privacy of the participants via data encryption and pseudonymization, and capable of being adjusted to diverse experimental settings. MakeSense allows remote monitoring and control and supports extensible APIs for integrating COTS or self-developed sensor suites. The use of the IoTX benefits from widely available commodity sensors and industry-standard Wi-Fi BLE radios, which provide flexibility and ease of setup in deployments. Flexible solutions for storage and visualization enable real-time monitoring and high-quality data collection. The data collected from the IoT devices can help the researchers understand the flow of indoor activities and validate reasoning about the underlying practices, together with the information obtained from other methods such as time use diaries. Thank you all for watching my presentation.